Thank you, Philip, for introducing the concept of resilience, because it's very important. And as you mentioned, you can find it in different fields, but for buildings and for cooling especially, it's we started to work on it heavily, and there is still potential for more work. In this presentation, actually, I would like to talk about new approach with novel overall indicator to assess resilience of thermal performance in buildings. My name is Mohamed Hamdy, and I'm associate professor at Norwegian University of Science and Technology. I'm working mainly on building performance simulation and optimization. So now we talk about new indicator to be used by simulation tools to make assessment. So before I start to show or introduce this novel indicator, I would like to mention about, or to give a background about a standard way to design our buildings. So if we're going to make a design for buildings, we make a lot of assumptions regarding to weather, regarding to heating system, how building can be used in order to assess the thermal performance of the building and energy performance of the building. And of course, there is a lot of uncertainties, but we do that based on a standard and some given inputs by standard of each country, different. Those assumptions, they don't consider resilience and how to be quantified. So now if we're talking about the concept of resilience, we see here probability versus impact on a y-axis. So usually we go to make assessment for high probability and low impact. This is what mainly standards focus on. But now we're talking about low probability, like events come to the building and it could have a very high impact. So resilience, by definition, focus on low probability and high impact scenarios. And it's very important to be considered to save our investments, because building is a big asset with a lot of investments. So we have to pay a lot of attention how to be designed and how to be resilient to life. So the new thinking here is to pay attention to disruptive events. And we have to know that also disruptive events, even resilience focus on low probability, but even these events going to be more and more frequent, higher frequency. We can see it by different reports regarding to cold weather and also warm weather. In this annex, we focus more on cooling system and warm events, for example. But I like to show in this novel approach, it's a very generic, so it can fit for assessing resilience for different events or disruptive events, which can be categorized to be natural disruption or technological ones. Natural can be related to weather, related to hydrological, related to climate, can be related to pandemics or biological. And technical can be about central failure or specific, like power cuts or failure in some system. So if we're talking about resilience, we have to say resilience against what? So we have to choose against which one of those disruptive events we talking about resilience. After that, we have also to choose the key performance indicator. We talk about thermal performance. We're talking about usually thermal comfort and energy consumption. And for buildings, in order to say it's a resilient, it has to have ability to prepare for the event before it comes, and also to absorb the event once it came, and to adapt that and to recover from the event. So, and even by recovering, and if we're talking about cycle of events, then we can talking about active learning, and the building can be smarter to prepare for a next event. So here we're talking about this definition. In this paper developed by my PhD student, Shabnam, and I am as a supervisor of her, we did this work about how to quantify resilience. We introduced a multi-phase test framework to consider different abilities of resilience. We also consider in this framework multi-zone building, because if we're talking about building, it has different zones. So we cannot focus on one zone and say the building is resilient. We have to consider different zones, and different zones in different buildings have different requirements how to be considered. Finally, after we have a key performance indicator, we introduced how it can be used to give a label, like we have energy label system, but also we introduce a labeling system for assessing resilience. So it can be in future certificates of buildings. If I'm talking about initial multi-phase resilience curve, as introduced here, initial state and then disruptive come here, and then building recover, and then it takes time. So here, this example is given for cold weather, like if you have set point here, and then in this yellow range, it's acceptable level based on the standard, and the orange one is habitable, and the other one is uninhabitable. It means it's no way to live in this condition. Similarly, we apply the same approach for warm or cooling system and warm events. So, but this paper introduced the concept on cooling for buildings in cold climates. Similarly, it can be applied for warm climates. And here we have to put different thresholds to assess performance. So if there is degradation in the performance, it can be different levels. And at different phases. So most important to assess resilience by the framework is not just to say the degradation of performance to this limit or this limit, but also the exposure time at each time step, how long it takes. So the first part of there is exposure to the event, maybe people can be okay somehow, but if the time is extended to say segment 2, people suffering more by having more time. So, and the same happened when we talk about this second level, about habitable level. The same, we have two different segments for uninhabitable, and the same for recovering. So in the end, we have like 9 segments or parts to be considered differently. If you can see, for example, if you have exposure to bad condition, like bad climate, indoor climate, for example, here, if you're talking about segment 6, people suffer more if you are in segment 1, for example. So we gave different weight for different stage, considering that for different levels, considering the 3 different stages of hazard. So by this we assume that the penalty for this phase 1, it's 0.6, and for recovering 0.4, because people recover and go to better. And for hazard level, we give different weighting factor, and exposure time also. Exposure time penalty here is larger than here, and here is larger than for segment 6 is larger than segment 4, for example. So that's what we have considered. The other issue which need to be considered is multi-zones, because if we're considering buildings and we take thermal comfort as a performance indicator, not for resilience, but to assess the comfort inside the building, we know that there is different comfort levels. It can be static or can be adaptive, like what you can see here in this chart. And also for different zone, the criteria can be different. So by having indoor overheating degree, which shows the difference between the condition and the limit which fit for different zone, we consider the indoor overheating degree for each zone separately, and then combine all together. This is how we can quantify it for different zones. After that, we consider the degradation of this indoor overheating degree for different phases of resilience. That means we have also different phases and different segments. So this is another accumulation to consider overheating or undercooling at all these segments. In the end, we introduced this weighted unmet thermal comfort. weighted unmet thermal performance indicator, considering 2 phases of resilience, 3 hazard level, and 2 exposure time for each hazard level. By having this new indicator, if we consider or we assess this indicator for reference design and then for the design we have, and we can see this ratio, and based on the ratio, we can have different like levels and for this label system. So we consider the same approach like used for labeling building based on energy consumption, but here we do it for resilience. So we select the reference building and then we select the building type of interest and then location, and then we apply this test framework which I introduced. After that, we calculate for both unmet weighted thermal performance for reference building and for the building under design, and then we consider the index and we can evaluate the label of this. Here it's we applied this approach for a case study where we talking about single family house. So the first phase, it was 1 day, and we made the framework to be 4 days, 4 days, and 1 day, considering different 4 phases of resilience. And the way we did it in this way, it's like test framework, and it's like test benchmark for different buildings. We have to test all of them under the same condition in order to compare and make benchmarking. So this is actual results of when operative temperature drop and recover at different building. And also we can test how battery and storage can make this degradation less in different phases, if we're talking about this phase or the second recovery phase. Here, if we have a photovoltaic which provides, like even there is electricity cut, that is the event we're talking about. But of course, if we have PV, we have free electricity during this disruptive event. That means we can be more resilient by PV. The same, we can be more resilient by battery. So we applied this approach with PV and with battery in order to see if we can test how resilience can be improved by this technology. I would like, before to end this, also to show that this another study. It's called Impact of Building Retrofitting of Thermal Resilience Against Power Failure for Air-Conditioned Buildings. So the previous one, I showed power cut for building in cold climate countries, where we introduced this approach. But after that, we apply the same approach for what's more fit for this annex about thermal resilience for air-conditioned building. So the same approach is applied, but here, when there is degradation or power failure, we see temperature go up because air conditioning doesn't work. So it's just the opposite, but the same exactly approach. We have also these 3 different levels. And when we applied, we made different design, like the building with air conditioning system with PV, for example, or the building has a passive design or standard design, or has phase change material, doesn't have phase change material. So we consider different mitigation measures for avoiding overheating. And we see here the leveling of all these designs are different. So as expected, a passive house with phase change material has more resilience than, for example, building traditional building without phase change material, for example. So the indicator succeeded to quantify the resilience of different designs as expected. This is what I like to, so in order to conclude, it's just like we introduced this generic approach to assess thermal performance of buildings. And the same approach can be applied for building with heating system or with a cooling system. So I would like to thank you for your attention and for next presentation, I would like to introduce my colleague, Aziz Lawadi from Canada. So